Yes, thank you for that introduction. You kind of killed off my first slide, but never mind. No, not you. My introduction. So that's how you can find me. All the slides are on GitHub. If you go to my GitHub account, go to talks, you get a copy of the slides with all the links and so on. So, and here's the book. Yes, right. Okay, we've done that. It does exist in paper form, but unfortunately you can't buy it anymore. Amazon has sold out. So they're now collector's items. Right, so what am I going to talk about? So I'm going to talk about, I was wondering, there are two blog posts that discuss the data I'm going to talk about. And I thought, well, you can go and read those blog posts. One of the frustrating things about analyzing data is people collect it the wrong way, or they collect the wrong sort of data, and then they don't analyze it very well. So I thought that there are probably lots of people in here who at some point in their lives are going to be benchmarking. And it would be useful to tell you or point you in the general direction, give you some buzzwords about what you ought to be looking at if you're going to do some benchmarking. So I'm going to quickly go through various points and issues and then get on to the examples. So collecting data, how do you do that? Ideally, it's a representative sample. Typically, people find, well, what data is easy to get hold of, which is convenient sampling. What data is convenient? And what systems do you have to run the benchmark on? Really, you want to control everything that's on the system so it doesn't interfere with your measurements. Oh, by the way, if anyone's got a question when I'm talking, please raise your hand and ask. Otherwise, I'll just rattle through these slides and we've done very, very quickly. And then if the pizzas don't arrive, we'll have to mill around doing something else. Now, one of the key phrases you need to know is design of experiments. If you search online for about how to run benchmarks, there are books called Design of Experiments. There are lots of blogs and Wikipedia articles about design of experiments. So if you search for design of experiments, that will narrow down the search for you and will take you to useful information. And the general rule about collecting data is the more the better. You can't have too much data. So what is a representative sample? It's typical code. You've got to ask who's the end user of the results. When you're reading papers by academics about when they analyze code and so on, they typically go to GitHub. There's loads of code on GitHub, let's go and get it. And that's really a convenient population for them to go and grab the data. A popular benchmark for measuring the performance of compilers are the spec benchmarks. You can go and download all the benchmarks and all the results. There was an organization for the embedded world, but now they've joined spec. So it's all within the same organization. So some more buzzwords for you. So design of experiments. If your variables interact when you're running the experiment, you've got various controlling factors in the experiment. How's the best way of selecting which values to set your variables? So some buzzwords you need to know: Latin squares, factorial, Black and Burnham. If you search on these keywords, it will give you suggestions about how to organize and how to select which variables to set. I have an example here. If there were 5 variables, there would be 32 different combinations of those variables, which might be too many variables for you to run. It would take a long time to run the benchmark and so on. So one way, you could run something called a fractional factorial experiment, where there would only be 8 possibilities. And that's one particular way of running the experiment, where you might have something low and minus might be low, plus might be high. This assumes that there are only 2 possible combinations. There are ways of doing this when there are more combinations. So I'm just whistling through this to point you in general directions. This is not really a detailed discussion about running experiments. So people who gather data, people go and typically do rather rudimentary analysis of the data. They take the mean and the median value, standard deviation, or they just produce some chart porn. And my experience is when I go out and most of the data I analyze, I get by emailing people saying, can I have your data, please? And about a third of the people just ignore me. About a third of the people say, oh, the data's on an old laptop. In other words, it's gone. And about a third of people email me the data. So a lot of the data I get, I manage to extract a lot more information from the data and tell people a lot more about what's going on, the processes going on, than they've done. Now, imagine if you spend a week or two gathering this data, and then if you use very simplistic methods, rudimentary methods, you're not going to gather much information. So I suggest you learn about regression modeling. And I use that extensively in the book, and there's a chapter on running benchmarks in the book and so on. The idea behind regression modeling is you fit a formula that specifies the relationship between variables. So for instance, you might measure compile time, might depend on the headers that are included, it might depend on the compiler that you're using, and it might depend on the version of C++ standard you're using. And when you've got this formula and you fit the regression model, you can see the impact of changing the compiler. You can see the impact of different kinds of headers, and it provides a lot more succinct information. Okay, so the first data, so that was the lightning tour of how to run a benchmark. So compiler benchmarking, people normally think of the quality of the generated code. This talk is actually about compile time. How fast is the compiler? So I read this article here on the Virtually Random blog compilation, and I was impressed by how much effort that this person had. There's no name on the blog. I couldn't find his name on the blog. So this anonymous person who writes the Virtually Random blog wrote this, did awful lot of work at gathering lots of data. I thought, oh, that looks like a very interesting collection of data. And so I left a comment on the blog post saying, where is the data? Can I get it? And he replied and said, yes, the data's here, and made it available. So I'm going to be talking to you now about this very data. And this is how I find a lot of data. I do occasionally run my own experiments, whether I gather data, but about 95% of the data in the book comes from other people, from papers, from me emailing people, from blog posts, or whatever. So this is what he wanted to do. He wanted to measure how long it took to compile time for each header. And he used 4 different versions of the C++ standard, 98, 03, and so on. He used, I don't know whether you treat VisualStudio 15 and 17 as 2 different compilers, and he used Clang, and 99 different headers. So the idea is he'd include a header, compile it. In fact, he compiled each one 128 times, which is fantastic because it removes a lot of the random effects. And to run through all the permutations and combinations took him between 10 and 24 hours. So that's a lot of work. That's a lot more work than your typical benchmark runner executes. So I was impressed by this, and I thought, oh, I'll get the data. Oh, and the data's available, and you can go and download it all. So there's the blog post where I give the details. So the question is, how are you going to model this data? What's a good model for this data of compile time? And there are 2 ways of looking at this. You can do what's called an additive model or a multiplicative model. An additive model, as the name suggests, is you add things up. So there'll be some overhead, we'll call it K, and each header will contribute. Sorry, yes?
Just to clarify, by that file, you just measured parsing, right?
Sorry, measured?
Just file parsing, like it doesn't do anything with the file, right?
Well, it's just a header. Well, it's trivial amount of code.
Okay, so just to parse. Okay, cool.
Yes, yeah, it's code generation for that, which is essentially parsing and semantic analysis and what have you. And then the compiler might add a bit in, and then the version of the standard might make a contribution. So that would be one way of modeling it. I'll come on to the second line in a moment. The other way is a multiplicative model. you would say, well, there's a constant, a base rate, and that a header modifies that by some fraction, and that the compiler, different compilers modify the base rate by some fraction, and that the language modifies it by some fraction. So there are different the two ways of modeling compile time. And okay. And you can also, there might be an interaction between the compiler and the language. And I happen to know there is, because when you analyze the data, you can very quickly try various combinations. And in fact, a better model than the first one is compile time is K plus a header, plus the compiler, plus the language, plus an interaction between the compiler and the language. So that's the regression model. So I'm skipping over how you fit the model and the technical details. These days with modern software, it's trivial to fit a regression model. It's a couple of lines of code and that's it. It just pops out. The hard bit is understanding the statistics and the model and the processes behind it and interpreting the data. So this data has been normalized, so that K is a 1. So this is saying, for instance, if we look across, that header assert contributes minus 0.65. Header WC type is minus, it's normalized around 0, it's balanced around 0. So header windows contributes 1.3 to that sum there when we're adding up that header X, you'd add the numbers up. I'll come to an example in a minute. And then looking down, here you can see the contribution of the different compilers, what contribution that they're making. And then further on down, you can see that the different versions, standard versions, by setting the command line option, the contribution that they're making. Yep. Question?
I'll just stand here.
Sorry, I'm not too familiar with this. Like, if it's a negative number, it means that compared to the mean one, it's better. So including assert is better than including mean one, or what does it mean?
Yes, so a negative number would mean it would be quicker, because what we're measuring is compile time. So a negative number would be quicker, and a positive number would mean more time.
You adding a header, it cannot make things faster. Like, so it's better than.
But there's a K. There's a
baseline.
There's a baseline, and that's saying that which is, it essentially sits in the middle, and you have a baseline, and a header might subtract away from the baseline, or a header might add to the baseline.
Okay, thank you.
So these numbers, it's really about relative values, because obviously if you ran on a different system with a faster CPU or whatever, the numbers are going to change. So the reason it's been normalized is you want to have a relative value. How much faster is this compared with that? So if you look at C11 plus C++11 and C++14, you can see that the C++11 is faster than C++14. So it's a relative contribution. Because the author ran it on his machine, and you would say, well, what difference is it going to make on your machine? And if you took his numbers, you're going to have to normalize them anyway.
It's smaller. How is it faster? How's C++11 faster?
I don't know. I'm just reporting the figures.
I mean, the number is smaller that you have.
You mean the number for C++11 is smaller than the...
Bigger than C++14 number, right? Oh, my stupid. It's a negative number.
No, this number here. So 11 is 0.03.
Ah, yeah, look at it.
And this one here is what? So it's bigger.
So okay.
And if you, yes, and here's Visual Studio 15, here's Visual Studio 17. So 15 is actually faster than 17 because you're taking away slightly more. So this is an additive model. And then you have an interaction between the languages. So this is Visual Studio 15 interacting with language C++ 11. And this is Visual Studio 15. This is only a subset of the numbers. I had to get it all on the slide. And so what you do to do the calculation. So if we were taking W chart H as an example, with Visual Studio 15 and C++ 11, you take the numbers, add them all up, and you get the result, 0.27, whatever. So this is the additive model. So then the advantage of this approach is you can change rather than a huge table in his blog post, he creates this huge table of all the headers and all the compilers, and you look down, you can see the contribution of the individual compiler. You say that compiler has that overall effect. So it's pulling out all, each component, and you don't need to have these huge tables and plot these bar graphs and what have you. There's a straightforward there's a straightforward equation. I mean, all the people in this room understand equations. So this is an additive model. You're adding the numbers. But then you might say, well, compilers, compilers going to change the result by a fraction. Compiler is fractionally faster or fractionally slower. So it makes more sense to do a to multiply the effect of the compiler and the language.
Question over here.
Yeah.
Hi. It's a while since I've looked at this stuff, but from what I remember from multiple regression models, some things that you're interested in are, what's the, you've got some measure of how well the model fits the data.
Yep.
And also there's kind of a lot of art towards figuring out which parameters are significant and which can be dropped. Are you going to move on to that at some point?
No, I was going to keep it simple. The blog post talks about that. But I thought, no, since this is probably new to everybody, I don't want to dive down too far into the details. Okay. I can switch to the blog post and go through it, but yeah.
Okay. Thanks.
Yeah.
Yes, hi, thank you. I'm sort of failing to understand why the header is a factor in those measurements, because surely if I want to choose a compiler or a version of the language, I can understand, I can choose that, but I'm not going to choose anything based on what header I'm going to use.
The author of the blog post thought it was interesting to find out the impact of different headers on performance of compile time. And so he did these measurements. I'm not saying he found them interesting, so he made the measurements. But now, in practice, there might be an interaction between headers. Sorry, is that no. There might be an interaction. So if you include one header, it will affect the performance on the other header because macros have been set or various other things are going on. But so this is the nice, base, simple way of doing things. Take a header, compile it, measure it. The next step would be to benchmark multiple headers, and then compare the impact of different headers or combinations of headers against the base rate. Yeah.
Naughty bit of code.
Yes, yes.
Doesn't it matter a little bit like what the code is using from the header? Like if there's some template stuff going on in there.
Well, it's not using anything, so the
template's going to have a big impact on compile time, right?
Sure, but so it's measuring the effect of including the header, and the header doesn't do anything. You're not using anything of the header. So it's the simplest possible measurement it could be.
Sure. I'm trying to get at what's it actually telling us. What's the purpose of doing the test?
His own satisfaction, I guess. Okay. So if you include a header, what is the smallest? What impact does it have? The base rate of it's measuring a base rate of including a header and doing nothing with it. That's it. It's a nice. If you were going to run an extensive set of benchmarks to look at this kind of thing, this would be the first thing you do to establish a base rate. You'd have a very small file, a minimal file, and include a header and not use anything from the header. And that would give you a base rate to progress to the next level. But he hasn't progressed to the next level. I suspect he was scratching an itch, and I looked at this and thought, "Oh, this is interesting data." I write a blog post, and I need things to write about every week, so I thought, "Oh, I'll grab the data." You don't normally get the sort of this well-run kind of experiment with extensive amounts of data. Most people do it. They grab a small amount of data and they don't do all the permutations and combinations, and it's horrible. This one is very clean and very simple. So I talked you through the additive model. The other idea is the multiplicative model, where the compiler makes a percentage contribution to the performance. And here are the numbers for the multiplicative model. So actually, this is measuring CPU clock cycles rather than time. Let's not go there. So the intercept, the 9.7 times 10 to the 8, is this number C. Is that number C down the bottom there? Is that top number up there? So you take that top number and then you multiply it by the impact of the header, the impact of the language. So coming back to the language now, we've got 7. The impact of C++11 is essentially no impact. 14, it's all around 1. So the impact of the version of the standard is fairly small. And if we look at the impact of the language, sorry, the compiler, where's the C-lang one? There's a few interactions going on. So if we then, so this is the example calculation again for wchar. That's how you would do the calculation. You take the numbers and plug them in. Now, I think a multiplicative model makes more sense for a compiler because you'd expect the compiler to have a percentage effect on compile time for a larger file. And I think it also makes it's a more sensible model for the standard version as well. The impact of the standard version will have a percentage effect on your performance. The header file, I suspect, is more of an additive issue, that particular headers won't change your compile time by a particular percentage. They will change it by a fixed amount because they are a fixed amount. So how am I doing? Okay, so that was the first example. So that's a quick zip through the calculation. You can go and read the blog post, goes into details. So this is a nicely run experiment. He had a specific goal. He kept everything simple. He ran all the permutations and combinations. He did it 128 times, not just 2 or 3 times. Okay, it took him 10 hours. So this is how to do it. How to run the benchmark. Unfortunately, he did the typical rudimentary statistics approach, and then I came along and did the regression modeling approach. But now, of course, you now know that you should do regression modeling, and regression modeling will allow you to extract a lot more data. Everybody nod. Yeah, good. Well done. Yes. Right, okay. So let's move on to the next example. This was another blog post, C++ versus Rust compile times. And again, a blog post. Is coding in Rust? What he actually meant was, is the compile time worse? And this time I have a name, Strager, and there's his blog post. It's S with it's a lowercase s. I spelt his name with an uppercase S, and he sent me an email saying, no, I'm lowercase. And there's my blog post where I compare the two. So this benchmark, his sample is, he took an existing C++ program, 17.3K of code, lines of code, 7.3K of tests, converted it by hand to Rust. And then, yes, people do. His argument for not converting more was it would take him longer. So, and then he copy pasted 8 copies, 16 copies, 2, 8, 16, 32 times to get bigger files. And then he ran every combination 10 times. So I guess the main issue here, I've got a couple of issues with the sample. The sample size is very small. It's only a few handful of Ks of lines of code. And when you look at how he ran the tests, because the timing data is in the data, he ran all the Rust tests, and then he ran all the C++ tests, and then he ran a few Rust tests again. The main problem with this is if there are background processes starting and stopping, they will interfere with the measurements. So the way this should have been done, he should have intermixed run Rust, run C++, run Rust, run C++, and so on. So that you'd expect this to have some impact on the results. So again, we built a regression model. I built a regression model, and there's the model. Compile time, E raised to the power copies, the number of copies. So the more copies you have, the larger the amount of source. And L is 0 if it's C++ and 1 if it's Rust. So you can see the impact of Rust, and then if you expand out those numbers, you get that table there, and you can see. And again, I've normalized it, and you can see as the amount of quantity of code goes up, Rust slows down faster than C++ slows down. You're all very happy with that, I guess. So, oh yeah, sorry. Copies. So rather than translating a C++, so the question was, what's this 181632? The rather to create a larger benchmark, he took copies of the largest file 8 times, 16 times, and 32 times to create more source code to benchmark, to compile to benchmark.
Same times, let's say.
Correct. Well, he copied it all into the same file and then copied that larger file. Yes. Yeah. So person at the back was asking about more sophisticated stuff, and there is the more sophisticated stuff. You might say, because it's a small benchmark, I hope perhaps you might not see those smaller numbers. Can we zoom in on, hang on, let me try and. Can we, what I want to do is I want to zoom in on that fraction of the screen. Oh, there we go. Thank you. Yes, just that bit. Here we go. You might say, well, how, here's the formula. What's the confidence interval on that number, on that 0.028? And in fact, the confidence interval here is 0.001. So and here it's 0.002. So if you want to get down into the details of confidence intervals, those are the numbers. And then when we talk about the copies again, so it's 1.2 plus or minus 0.01. Now, one thing you'll notice is that the Rust confidence interval gets wider and wider and wider. It gets much wider than the C++ interval. Now, one interpretation of that is that there are things going on in the background when the Rust benchmark was run that were not going on when the C++ benchmark was being run. How do I get out of this? Thank you. So perhaps when that Rust benchmark was being run, things were going on erratically, and that was introducing variability into the measurements, and that variability was not occurring when the C++ benchmark was being run. So that would be my first interpretation of that uncertainty. The uncertainty here, the greater uncertainty in Rust, the first thing I would do is I would go back and rerun the benchmark and intersperse the results. I wouldn't blame that on Rust, at least to start with. Yes.
Why wouldn't you pin the CPUs when you're running the benchmarks to
Yeah,
eliminate the outside interference?
That you could certainly do that, assuming switch hyper-threading off. Yeah, yeah,
No, isolate the CPUs.
yeah. That's certainly what one possibility. It could be other things going on. It could be other processes hitting the cache. You don't know what's happening. Yeah, it's much easier to just intersperse. If you intersperse, then you don't have to worry about those issues. Certainly, if you have greater control of the machine, you can lock the CPU, you can lock everything down. That's certainly an option. Yes. Okay. So talks usually finish by people saying they're hiring, and I'm not hiring, but I am interested in data. So here's my pitch. If you have any software engineering data, I offer to do a free analysis of that data for free. And the condition is that I make an anonymous version public because I publish all the data I talk about. So if you have any data, I'm particularly interested in human data rather than source code data. Come and talk to me. Okay, that I am done. I finished rather quickly. Peter, question at the back. Peter's arrived, so I'm safe.
So I would like to know, how do you check what model is the best one for comparing the data? For example, like you can be biased by checking the model. For example, like you can set up especially the parameters there, like K or header or compile, or maybe you are presenting extra constants or extra variables there, like to tweak here and there, but
Yeah.
you are biased.
Yeah.
You want to see the data you want to see. So like how to be sure that this model is actually objective?
There are statistical techniques that will tell you that this model is a better fit than that model. Yeah, you can abuse them. Really, it's your domain expertise. You've got to say, well, does it make sense to add contributions together, or for instance, add the contribution of a compiler, or does it make more sense for the compiler to make a fractional contribution to be a percentage difference? So it's your knowledge as a domain expert in how compilers work to say, well, my own opinion is that the multiplicative model is a better model of reality. So how do you think those two models map to reality? And that's your level of that's your expertise. And when you argue to people, you say, well, this is why I think this model is better. Now, you're quite right. I could have added more parameters in here and got a better and better fit by building this hugely complicated model. And I looked at it and thought, well, no, I'm overfitting. And there are techniques to try estimate when you are overfitting and not. The advantage of writing a blog and not having a boss is I can satisfy myself. And I thought, well, I can with a clear conscience, I can say that I think this is the best model because I'm not being measured in any way. It's just a blog. So it's my. People might, if your boss comes to you and say, well, we could do some better numbers here. Can't you have a better fit? And then there's pressure to put, more stuff here to build a more complicated model. And that happens all the time. You look at some papers and you think, oh, they've just added stuff in here because of this, that, or the other reason. Yeah, it does happen. Yeah. Try him.
My question is also about parameters, specifically in your additive model. So when you have this language Z, right, do I understand correctly that you have basically 7 different features, one for C++11, one for C++14, and then they're effectively binary, right? They're either 0 or 1, and then you have coefficients for all of them.
That's correct. Yes. Yeah.
Okay.
Well, yeah.
And the same for every header. So basically, in your model, you don't have just 3 parameters. You, in fact, have like 12 or more, and this is what you fit it.
Yeah, there's no continuous parameters in the model. All the parameters in the model are discrete.
Right. Okay, thank you very much.
One down here.
My question is about multiplication of source files. Different compilers treat different files with same content, could be as cached parts. So does it really works to treat this as real longer line of codes?
He copied it copied it 8 times into the same file. So the compiler, I guess the compiler could have figured out, oh, that bit of code is the same as that bit of code is the same as that. But that's such an unusual thing to occur. I suspect the compiler didn't do that. It just went ahead and blindly, oh, here's another function. Let's compile it.
Because if you, for example, change names of variables and function names, it could possibly work. But if you have the same file, same names of, it could be absolutely important.
Oh yeah, you'd have to change the name so you don't get name clashes. Certainly, that's true. So if you've got 2 functions called f, the compiler would complain. So you're going to have to call f and then f1, f2, f3, f4, and so on. So you've got to make a few minor changes just to get the thing to compile.
And does these functions been isolated, or they imported something into it, like use it external imports?
I didn't look into the details. His blog post explained what he did, and it works. So I assumed he made it work.
Because I read this blog post. It was like in Rust you have quadratic formula, in C++ more linear one, but like.
Yes, I wrote another blog post where I saw quadratic behavior in the compiler, and I thought, oh, and then that's kind of interesting. And I emailed them, and nothing came back. And I thought, well, do I want to follow this up? No, not really.
For me, it's actually super hard to believe, because like Rust code base could be really high, and when you have something quadratic, the compile time will be super long, pretty fast.
Well, presumably they've probably got some simple algorithm in their compiler, and that simple algorithm is acting as a bottleneck, and it's a quadratic algorithm. So if they went in there and looked, they go, oh yes, we're using a quadratic algorithm here. We shouldn't in the compiler. Yeah, I suspect it's something simple that they haven't yet. Oh, they probably have noticed now, but they didn't in the past.
Okay, thank you.
Yeah, we got
testing. This entire talk seems to come from people doing performance analysis really badly.
No, I think this one was fantastic.
Well, not as good as he could have done.
He could have done some fancy analysis, that's true. But the actual gathering of data, I think, was fantastic.
So with your knowledge, do you know if there are any sort of Bible resources out there that essentially act as a reference for doing performance analysis perfectly, so to speak? Because I've seen a couple, but they don't really cover the whole broad range of different sort of techniques that you need to employ or think about when doing performance analysis. It seems to be like
there are books on how to do performance analysis, including software as well. The performance analysis for software tend to be multiprocessor ones. If you search for performance analysis on software on Google, on Amazon, you'll find a few. I'm trying to think of some off the top of my head. I can't. They'll certainly be in the book. If you do performance analysis in the book, all the citations are there. The usual problem is resources. Your boss comes to you and say, I want you to measure the performance of this. Oh, and you've got to do it this afternoon. And you can't sensibly do it this afternoon. You need more time. And it's something that people do every now and again, and therefore they really haven't got much practice in what to do. And they look at how other people do it, and they say, oh, we get some numbers and then we average them, and that's what they do. Now, the data analysis I can do very quickly because I've had lots of practice. I've probably analyzed several thousand data sets, so I can just sit down and do it in about 10 minutes. It's very quick. But I guess the average person, it will take them a few hours because they've got to learn what to do. Then you've got to scratch your head and say, well, when you're making this kind of decision, You know, what should we do? I've got the advantage where I can look at what's happened in the past and say, well, this is what happened previously and that worked out well, so let's do the same thing. Yeah, in terms of the key word you want is design of experiments. If you search for design of experiments, there are some very good books called Design of Experiments that will tell you how to run. A benchmark is an experiment, and they will tell you how to design experiments, and you'll see how to run benchmarks.
Yeah, I think there's a really old book from like the 1960s or 80s, which is about design of experiments, and it has like a purple cover.
Yeah.
But to clarify, there is no sort of one universal God resource that you could just read.
Well, chapter whatever it is of this is.
I think it's chapter 13.3. I had a quick.
Okay. Yeah. So there's somebody at the front. Yeah.
Two questions. So the first one was, in the second experiment, couldn't you already tell from the variance that, I mean, just simplistically looking from the variance that it probably doesn't look right, that there is some other factor, the Rust compile time actually, rather than doing this statistical regression model first?
Well, what happened was originally I thought, oh, let's have a quick look at the data. And then I looked at it and go, okay, let's look at the variance. So that kind of came later, which happens a lot. You do some analysis and then you think up new ideas. I always lecture people and say, well, you have to follow this structured approach. And of course, I never follow that structured approach. Like everybody else, I just sort of dive in and start looking around, do all the things I tell people not to do. Yeah.
Sorry, follow up.
Yeah, he's got follow-up. Second
I
question,
also
yeah.
do not understand this regression model. Can you please explain it a bit more? Because I would have
Okay,
expected to like a different model.
so this is compile time. Is approximately, so erase the number of copies. So this would be 1, 8, 16, 32. Times, so there's a fitting number here, 0.28, plus that number times L. And L is 0 for C++ and 1 for Rust.
Why is it L? Sorry, why is L 0 and 1? Is it just
well, because you have, I could have written two equations, one equation for the C++ equation and one equation for the Rust equation.
Okay.
And this makes it obvious that this is the impact of Rust on the expression, and you've got an impact here as well. So in one equation, you can see switching that to 0 or 1, the effect on performance. So it allows you to compare C++ and Rust.
Okay, thank you.
I would find this talk more interesting for my work if it was about execution time, not compilers.
Okay.
Do you also focus on execution times?
Yeah. It's exactly the same principles. You follow exactly the same principles. If this was a benchmarking on compiler performance, you'd go through exactly. You design it, the experiments. You gather your data, representative data of benchmark programs to run. But the spec benchmarks are compiler performance in terms of quality of generated code. And you go through all this, and you'd have one of these models, and it's all exactly the same, except rather than header, it might say benchmark, and rather than the standard version of the language, it might say compiler option, whether it's 01, 2 or 3 or whatever, 0, 2 or 3. So it's exactly the same. It just so happens this data is about
Compiling.
yes. And so if you go and search for this wonderful blog here, Shape of Code, there are posts on measuring the execution time of compilers and analyzing them.
Thank you.
Okay, thank you.